So we're moving on to chapter 4. So this is where we're talking about isomerism, and cyclohexanes and cycloalkanes and whatnot. So just to start off, just what is an isomer? You could say it's just gonna when we talk about that, it's just we're talking about the relationship between two molecules. So it's no different than if you're talking about, within your family, if you're talking about siblings or cousins or it says your aunt, stuff like that, right? Stuff like that. So it's always going to be between two molecules, stuff like that. So, but for isomers, what it is you have the same formula, but the arrangement of atoms is going to be different, whether it's just in space or if it's completely different or whatnot. When you're talking about isomers, you're talking about different rearrangements, but they're always going to have the same formula. Okay, so the first one is probably the easiest. It's probably what are called conformational isomers or conformers. They're the exact same molecule, they're just drawn differently. Okay, so with this one here, just let me draw this out. All right, so you can always check to see. Usually, if you check the carbons, it's fine. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So they have the same number of carbons. If they have that, then you're probably going to be fine. But if you notice, with this here, when we talk about finding the longest chain, right? For here, it's pretty obvious, right? So it's 1, 2, 3, 4, 5, 6, 7 here. So here's the longest chain. Okay, but for here, right, you have to go down the side chains, right? So 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7. Okay, so here the longest chain is going to be right here, right? So the longest chain is to be the same, but here, right, you have the same. Right, you have an isopropyl group and a methyl, right? But for here, right, the numbering is going to start 1, 2, 3. 4, 5, 6, 7, right? So your methyl is coming off of 2, isopropyl is coming off of 4, right? But if you here, right, the groups are on this side, so you're going to start numbering here. So 1, 2, 3, 4, 5, 6, 7, right? So again, you have the methyl at 2 and the isopropyl at 4. So all we've done is, flip the molecule, from going from here to here is just flip the molecule over, rotated a couple of bonds, and that's it. But it's the exact same molecule. Okay. So those are called just conformational isomers. It's the same molecule, it's written like that. And if you were to go in and draw and get the name of this, you would see that it's the same. That's one of the nice things about the organic naming, is that no matter how it's drawn, it'll always give the same name. Okay. So one of the ways that you can visualize these are what are called Newman projections. Okay, and so the way these things work is that you can come in here, and what you're doing is you're looking directly down. So you're going to be looking directly down a bond, okay, and stuff like that. And so, I don't know what just happened there. Stuff like that. And so you're going to have the carbon in the. In this case, the way that they rotate, they went going from here to here. What you're doing is you're having a carbon in the front and the carbon in the back, okay. Stuff like that. But if you look directly down, you're not going to be able to see the carbon in the back, but you're going to be able to see the groups that are coming off of it. Okay, so here the X groups are these ones back here, while the Y groups are the ones out front of here. Okay, so these Y groups are emanating from the front carbon here. Okay, front carbon here. Okay, while these X groups, which would be back here, are emanating from the back carbon. Right, you notice how you can't see the bonds. Right, in theory, you wouldn't be able to see it because the carbon in front is being able to obscure them. Okay, and so we're going to look down these bonds, and it's easy to see it. The reason why we do this is so that the bonds itself, you can see the interaction. You'll be able to see the interactions. Okay, now one just sort of point of vocabulary here, we call what's called the dihedral angle, and it's really going to be the angle between something in the front versus to something in the back. So the angle between this red ball here and this blue ball here, right? That's 60 degrees. Okay, between this red one in the front and this green one in the back, right? So that's 180 degrees. Okay, we don't talk about these guys. on the same carbon, right? We're really going to be talking about one carbon versus the one in the back. Okay, and so if we wanted to draw these, okay, draw the structure from the Newman projection, okay, and so if we start from here, okay, let me do the same orientation here. Okay. So if we start from this, we're saying is this carbon in the front, right? So we have two carbons, right? So that the one in the front and then the one in the back. Okay, so the one in the back. The front one is going to have a CH3 coming off of it, and then two hydrogens. Like that. Okay. The one in the back is just going to have three hydrogens coming off of it. Okay, so this is the one in the front, right? This is the one in the back. Okay, the one in the front's got this methyl hanging off of it right here. So what we've drawn is essentially propane. Okay. Okay, so what we're going to be doing is we're going to take these things and see how the interactions change as we say put one of these, say, the back one fixed, and then we're just going to rotate through these and see how they interact with each other. Okay. Remember, with carbon-carbon single bonds, you can get free rotation about these, so we'll see how the interactions go. Okay. Okay. So there's there's a couple of terms you need to know. So the first one is that when there's conformation, where everything is sort of in between each other, right? So the ones in the back and the ones in the front are sort of, you sort of see it like that. Okay? Notice how this is the conformation called staggered. Okay, stuff like that. So everybody is, everybody is going to be, maximum distance between it. Okay. Now, if you do this and you say it like that, so everybody's on top of each other. Okay, from front to back or whatever. This is called eclipsed. Okay, there's going to be a lot of these guys here are always going to be able to feel each other. Okay, so there's going to be some interactions there, and 99.999% of the time, if you're looking at which one's the more stable, it's going to be the staggered version, right? Because you're basically putting more distance between these two, stuff like that. So staggered is always going to be less energy than eclipsed. Okay, and so if you were to rotate this around, right, so with that, so you start off with the staggered. Okay, let's say you hold the back one fixed, you rotate the front, right, then it goes eclipsed. So now you've got this eclipsing, this eclipsing, this eclipsing, and then you go back, you rotate it around a little bit more. Now it's staggered, so you're at lower energy. You got rid of those. You rotate it around again. You've got eclipsing interactions here. Staggered, eclipsed, staggered, eclipsed. Staggered, eclipsed, and it just keeps going around. And so if you were to map out, and so we know what this energy is. Okay, so it'd be this eclipsing, and you literally just add them up. This book doesn't have you add these up, but that's what you would do. You just add these individual ones, and it would go, low energy because they're staggered, high energy, low energy. Because the eclipsing with staggered, with hydrogen staggered, there's no interaction, right? Because the hydrogen is pretty small, but there is when they're eclipsed. So it's going to go up, down, up, down, up, down, up, down. Okay, and so this energy here is what's called the barrier to rotation. So, the molecule is going to be able to, it's going to want to live down here in the wells, right? Because it's the lowest energy. In order to get over to here, right, it's got to go over this energy hill, right? So it's going to take some energy, right? Because it's, just think of you walking over a hill, right? It takes energy to get over that hill. But now once you're over here, you can slide down, and it goes pretty quickly. So you got to pay that energetic price to get it down here. Okay, and stuff like that. So that's going over here. And again, this is called the rotational energy barrier. Okay. Now, you can have, if you have groups other than hydrogen. So let's say these green ones here are, I don't know, chlorines. or I guess bromines here from this. Okay. Obviously, when they are eclipsed like this, you're actually, because say the bromines are going to be really big fat atoms, there's going to be high energy. But the fact that but even when they're like this, okay, when they're staggered, okay, you're going to have less energy, but they're still going to be able to feel each other. Okay, you can sort of see this here, where they're sort of feeling each other. This here, when you're talking about non-hydrogens, okay, hydrogens staggered, there's nothing there. But when you have two groups that are non-hydrogens that are staggered right next to each other, this is what's called a gauche interaction, and there is going to be some penalty you have to pay in order to be able to do that. Okay, so that depends on what the groups. You go to the big book of gauche interactions or whatever it is and look it up. Okay, some poor graduate student had to measure that. Okay, the best configuration is when this bromine here and this bromine here are 180 degrees from each other. Okay, not only are they eclipsing, okay, or excuse me, staggered, right? Everything's staggered, but they're the farthest apart that you can get. Okay, and that's what's called an anti-conformation, and that's how you really want it, the molecule really wants to be able to do is you can sort of see this here where one bromine is pointed this way and the other bromine is pointed that way, and everybody's happy. Okay, and so if you track these, okay, so if you start like this, okay, you're going to be at the lowest amount of conformation energy. You go here, you're going to get all these eclipsing interactions. Okay, here. But when you're going down here, yes, these guys are staggered, but now you're starting to get this gauche interaction, okay, which is bad. Okay, so you have to pay that penalty. So you're not going to be able to get all the way down. You're going to have to pay some penalty. Now, when you go here, it's going to be the most energetic. Okay, you're going to pay the highest penalty because you have two giant groups sitting right next to each other. So not only are you paying the normal eclipsing fees or whatever, you're going to have to also, you've got even more of it because these two guys are eclipsed. Again, when you go to here, it's gauche. You're going to have to pay that gauche interaction. Here, eclipsing now won't be so bad, right? Because big to hydrogen, it's not so bad. Stuff like that, and then you're back down to your anti-addition, your anti-conformation. Okay, stuff like that. So. Okay, so they're just conformational isomers of each other, the gauche and the anti-forms. Okay, so but the anti-form is going to be the lower energy. It is going to be the preferred form. Okay, and that's actually why we do a lot of the zigzagging. Okay, because what it does is the zigzags actually put all of the carbon atoms, if you line them up, they're going to be anti to each other. Okay, so like if you look at CH3, CH2. CH2. If you draw it like the zigzag like this, okay, you can sort of see this methyl group, okay, is pointing this way, it's pointed that way, and this methyl group is pointed that way, which represents it to being into in an anti-configuration. So this is really how it wants to be, okay, to minimize the interactions. Okay, next up, we're talking about these cycloalkanes. Okay, and so it turns out that, and the book goes into great detail on these heated combustions, and basically what it's saying is you could figure out, they're able to figure out the more energy it gets out of there, that means the more energetic it has to be to make it, right? So you're gonna have to put in energy. It's much less relaxed and stuff like that. And so it turns out that cyclopropane, cyclobutane are going to be, they have a lot of energy of combustion because there's a lot of strain associated. We'll talk about that in a minute. But as you get down closer to the cyclohexane, so 6-membered ring, okay, you're at a low point, okay. And actually, if you go in here to the cycloheptane, you actually go up a little bit in strain, okay. The reason why it's the most stable has to do with what's this chair configuration that this cycloalkane can adopt. Okay, let me build this in here. Okay. Oops. Okay, and it looks like this. Okay. Hopefully you can see this. It's kind of hard to see in here, but basically what's happening is there's sort of a part of this where, like in this one, like your head's up here, right, your body would go down here and your feet would come down here. Okay, so it's sort of, yeah, there you go. So your head would come up, so your head's at one end, your body's at the other, and your feet's at the other. Okay, so by that, just like a lounge chair. Okay, but the nice thing is when you get this, okay, and you can sort of see this. Let me see if I can get to this so you can see it. Oh, let me do this with the blue ball so you can kind of see it a little better. Notice how, I mean, it's sort of an old kit, so it's a little wobbly. But basically, when you get this in here, you get a completely staggered configuration. Okay, you can kind of see that here. Okay, everything is completely staggered. This is sort of an ideal way of looking at it. But again, everything's going to be staggered. You're going to have that sort of gauche interaction here, but that's okay. That's all you're going to have to pay. Okay, so with that, this is basically everything's going to be nearly ideal. Okay, for this thing. Okay, for cyclopentane, what's happening? Right, 5-membered ring, it can't quite get out of that. Okay, so with that, so it's partly staggered. It's not completely staggered, but now you're starting to get a little bit of these hydrogens here and here, to be able to go, and the gauche interactions between here are going to be much bigger because they're closer together. Now it can sort of pucker a little bit. Okay, so you can sort of think of like you have an envelope. You know how like the one flap is going to sort of come up. It sort of kinks one carbon out of the plane, and that helps to relieve some strain. Okay, just like if you're standing up, right? If you put you raise up 1 foot, right? It kind of takes the strain off a little bit, and that's what this does. It puckers a little bit, but there is more strain associated with a 5-membered ring than there is a 6. Okay. Now with cyclobutane and cyclopropane, right, you're getting less and less and less staggered. Okay, so that the cyclobutane, the 4-membered ring, right, is almost completely eclipsed. Okay, you can kind of pucker a little bit to get it out of there, but by the time you get to the cyclopentane, everything's completely eclipsed. Okay, and there's nothing it can do. So you're paying a major penalty to be in these two configurations, which is why they're so difficult to make. Okay, stuff like that, and so the most stable is going to be the 6-membered ring. Okay, as you get away from that, you're going to pay a little bit of a price. Stuff like that. So you can, we talked about carbon-carbon bonds having single bonds having free rotation, but the problem with is that you're somewhat fixed in a cycloalkane. However, you do get wobbles, right? You can see this with your model kit, right? You're going to get some wobbles around, okay? And so what actually happens is you get this what's called pseudo-rotation where it wobbles. Okay, but so what you could do is you could take the one that's pointing this way, you can move it down here and take this one and move it up. Okay, and so you can get some wobbles in there, but it's not true rotation. Okay, so they call this pseudo rotation. Okay, and this has pretty profound effects, and we'll talk about it in a second. Okay, but the first thing you got to talk about is what's called axial and equatorial. Okay, and so you can sort of think about this as a globe, right? So with that, and so. So if there's a globe here, right, so these guys here are pointed towards like the North and South Pole. Okay, these guys here, and here, as long as this one, yeah, these are at the North Pole, these are at the South Pole. Okay, so like that, and then you're going to have these ones around the outside that are towards the equator, the equatorial. So this is a equatorial. Okay, so let me draw this. Okay, so. Okay, so you're going to have an axial. Okay, so the axials are here. Oops. Okay, and so these are either going to be pointed, like in this case, these guys are going to be pointed up, and these guys are going to be pointed straight down. Okay, now one of the nice features about these is that if you look at the carbon-carbon bonds here, okay, notice how they point down. They always point towards the axial. Okay, so here, right, the axial is pointed there, right? Here you can see it too, right? So the carbon-carbon bonds are sort of pointed up. Okay, so that means that the axial is pointed up. Here again, notice how the carbon-carbon bonds are basically pointed up, right? So that means the axial is up. Same thing here. Carbon-carbon bonds are pointed up, so that means the axial is up. Here, I mean, it's a little hard to see, but these are sort of pointed down. Okay, so that means the axial is down. Axial is down. Okay, but if there's always going to be an up and a down for here, right? So your equatorial is going to be sort of sticking out, sort of out to the side here. Okay, and you sort of in the middle, you can sort of do your best, right? So if this is going up, that means so this is axial up, this is equatorial down. Okay, this is axial down. That means equatorial is pointed up. Axial down. That means equatorial up. Okay, axial's up. That means equatorial down. Okay, so the equatorials are going to be sort of pointed off to the side. They're going to be slightly up or slightly down, right? But basically, they're going to point to the side. Okay, the axials are either going to point to North Pole or South Pole. Okay, equatorial is going to be around the middle. Okay, they're going to be slightly up or slightly down. Okay, so for that you can sort of see these here. Okay, the reds are in the axial. When I swap the colors, but right, the axials are going to be here, right, north and south. Equatorial is going to be around the inside. Okay. Now it turns out, because life can't be easy, with these pseudo rotations, you can get what's called a chair flip. Okay. So the way you do this, and the way that I like to draw them is, we'll talk about a little bit how to draw these cyclohexanes, is to start with the 4 in the middle, put one at the top, one at the bottom, just connect your dots like this. Okay, and so here we go. So it's going to be, say, 1, 2, 3, 4, 5, 6. Okay, and so what happens is I'm going to put these. Now I'm not rotating them. What I'm doing is I'm grabbing this one and rotating that down, and grabbing this one and rotating it up. Okay, and so this is still going to be 2, 3, 5, and 6. But now what's happened is the one is up here, okay, and the 4 is down here. Okay, so that's all that's going on. So you can sort of see this. Sometimes you see it where it's sort of cocked a little bit. You sort of see it like that. It's still the same. I like drawing it like this, especially when you're just starting, because it's a little easier to see. Okay, it's a little easier to draw, but it doesn't really matter. Okay, so actually these are actually these aren't resonance structures. These are actually equilibrium from each other. Okay, so this what happens, right? So you take one end. Okay, so for here, right, you take this end and you rotate it down. You take this end and you rotate it up. Okay. Stuff like that, and so stuff like that. So and then you go backwards, right? So you take that one, rotate. Okay. So this is what's called a chair flip. Okay. Right. It's in the chair configuration, right? So your head's up here, right? So you're all happy, right? It's a really long neck, right? So your body's here, and then your feet go down here, and then your little brother comes in here and grabs this end, pulls this down, pulls that down, and now your head's down here, and then you're sad, and now your bodies are up there, right? Stuff like that. So, but it's called a chair flip, stuff like that. So, okay. So the consequences of this, okay, and so let's look at this. So, okay, so. So let's say you start with, we're going to do this backwards from what I did over here. Okay, so let's do it from here because this is a little bit easier to see. So let's say you've got a bromine, you got yourself chlorine. Okay, so here, right? So this is okay. So your so your carbon-carbon bonds are pointed up, right? So that means your axial is up. So this is axial, okay, axial up, okay. Which chlorine, right? So it's equatorial. So now it's equatorial down, okay. So let's do 1, 2, 3, 4, 5, 6. Okay. So now we're going to do the chair flip. Okay. We're going to rotate that down. Okay. I'm going to rotate 4 up. Okay. So here we go. So That's down. So this was 2 and 3. So 1 is here. Okay. 5, 6. So this is 4 is here. Okay. So now what happens is, right, so now the carbon-carbons are pointed down. So what's down is in the axial position, right? So now notice how this is down, so that means the chlorine is now axial down. Okay, so that means the equatorial is this way. So here the bromine is equatorial up. Okay, so the ups and downs stay fixed. It's just the axial and equatorial switch. Okay, with the chair flip, all the axials become equatorial, all the equatorials become axial. But the up and down thing does not change. Okay, if it was up on this side, it's up on this side. It's just, it becomes now becomes equatorial. Okay, so with that, that's going to become important down the road, right? So equatorial becomes, equatorial up becomes axial up, axial down becomes equatorial down. Okay, so with that, that's what happens. Okay, so with that, so be careful. Okay, so you can get partial flips. Okay, so let's say you're like this. Okay, let's say we move that up. Okay, now before we get a chance to move this down, okay, you get what's called the boat configuration, right? So it kind of looks like, it'll look like a paper boat, like that. Okay, so with that, the problem is, you kind of see that here. The problem is, notice how you have these two chlorines, right, or these two chlorines, hydrogens here, right? They're facing each other, and they can start bonking into each other. Okay, this is what's called a flagpole interaction. Okay, that's bad. Okay, and 99.99999% of the time, the boat configuration is going to be the least stable. So if you have a boat versus a chair, with some very, 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 very notable exceptions, it's going to be the chair conformation that's going to be less, the more stable of the two. Okay, you have a lot of eclipsing interactions here, so with that, it's not good, stuff like that. But it has to sort of go through it in order to be able to. It has to go. If you're going from one chair to another, right, you have to sort of go through this boat configuration to get over there, right? So you flip in one side, and then before you can flip into the other one, it's in a boat configuration. Okay. Now, how do you draw these things? I've sort of been showing this, but the easiest way that I found is to start with your 4 middle carbons here, connect those, okay? And then it doesn't matter which side, so let's put it on this side here. One up, one down, right? It doesn't matter which one, okay? And there you go. That's going to be the easiest way to do it, okay? Start with the 4 in the middle, and then put a dot up on one side, a dot below on the other, and then just connect the dots. That's all you got to do. Stuff like that. So that is a perfectly legal cyclohexane. Okay. Now, it'd be great if we just had to deal with cyclohexanes, but we don't. Okay. So with that, and so if we have like this, right? So with that, so if let's say we put a group on here. Okay. So let's say this is a methyl group. It doesn't matter. Bromine, methyl, doesn't matter. Okay. What you want, okay, is to have this, to have the big group equatorial, okay, because if it's axial like this, okay, what happens is you actually get, so let me draw it here. So even though the hydrogens, okay, so let's say you have a bromine here, you're still going to get these interactions here and here, okay. So with that, that's not good, okay. But when we do the chair flip, okay, this now this was axial before, right? Now it's going to become equatorial, right? Equatorial. Now it's pointed away. Okay, so when we do the chair flip, okay, it's pointed away, and so now there's no interactions with it. Okay, I can see this. Okay, and so that's good. Stuff like that. And so what you really want to do is you want to get as many things in the equatorial position as possible. Certainly the biggest things equatorial. Okay, and so you were to have this 1-3, so it's 1-3 interaction, right? So you're going to have, here they have a methyl group, it's going to be interacting with these bromines. Okay, and the bigger the group, the more interactions you're going to have. But when you put it into here, into the equatorial position, those all go away. Okay, and so you can see this, right? So if it's just hydrogen, right? So there's no real there's no real preference between the two. Okay, so it's 50-50. As soon as you put a methyl group on here, it stays 95% of its time here, and as that gets bigger and bigger, right, it creeps higher and higher. If isopropyl group, you have 97. If you have a T-butyl group, it spends 99.98% of its time in equatorial position. So this is, if you want to lock it into a particular position, you can, so that this T-butyl group is going to be locked into the equatorial because it's so massive with that. So, okay, but pretty much so with that. Okay, and so one of the things, okay, so with that, so if we get what are called okay, so that's for monosubstitutes. So you have monosubstitutes, it's pretty easy because you just put it into equatorial and everybody's happy. Okay, with disubstitute it becomes a little bit more complicated, but the first thing we have to talk about is cis and trans. Okay, so remember, cis and trans do not equal axial and equatorial. You can have cis where both things are equatorial. You can have cis when both things are equatorial. You can have cis when one's equatorial and one's axial. Doesn't matter. Axial and equatorial help you figure out if it's cis or trans by telling you which one's up or down, but they're not the same thing. Okay. Remember, cis is they're both up or both down, and trans one's up and one's down. Okay. So like that. And so if you're looking at it from top view, typically what we say is if it's a wedge like this, it's up. If it's a dash, it's down. Right. So this is up, up. Right. So with that, so that would be the up, up is cis. Right. So here's down, up. That's trans. Okay. It doesn't matter if they're axial and equatorial. It does not matter. Right, so with that, so with that, but they're both up, cis, both down, trans. Okay, and sometimes you do what's called a Hayworth projection. Okay, where everything's kind of flat. Remember, it's not, but this is an easy way to see it. So with that, but the so for here, right, they're up, up, and one's down versus up. Okay, stuff like that. So okay, but the problem comes. Okay, with disubstituted things. Okay, so what it's going to do, right? So if you have a cis 1,3, you have cis 1,3 dimethylhexane or cyclohexane. Okay, they're both going to be up. Okay, so here up is so here. Okay, so okay, so we're going to say this is 1, 2, 3. 4, 5, 6, right? So with that, so here, right? So notice how these things are pointed down. Okay, so that means the axial is down. Okay, so that means the equatorial is up. Okay, so let's say they're both up, right? So that would mean the CH3 is here. Okay, and here again the these guys are pointed down, right? The carbon-carbon groups are pointed down. Right, so that means that the axial is pointed down. Okay, and so since this one is pointed up, that means that methyl group is also pointed up. Okay, so they have to both be up or both be down here. Okay, and so here they're both equatorial. So that's fantastic. What would happen if we did a chair flip? Okay, right. So we go right. So 1, 2, 3. Right. So it becomes 1, 2, 3, 4, 5, 6. Right. So now all the axials and equatorials become switched, right? So this is still up, okay, but notice the carbon-carbon bonds, right, are pointed up, right? So now this becomes axial, okay? Here at the 3 position, again, the carbon-carbon bonds are pointed up, so that means that the this methyl group, which is the up, is also axial. So now you're getting some really massive interactions here, okay? If you do the chair flip over to this side, they both become equatorial. Okay, so it's going to want to be in this position here. Okay, the problem comes is if, let's say, this was trans, right? So we had the methyl group down here. Well, this is axial, one equatorial. Okay, let's do the chair flip. Well, then we still have one equatorial and one axial. There's no advantage of being in either position, right? So that means that they do it equally. Here, it's going to spend almost all of its time in this position. Here, with the trans 1,3, it ends up being that they spend equal amounts of time in each one. Okay, and so if you look at this one here, okay, so if you have an up T-butyl group and a down methyl group 1,3. Okay, so here, in this configuration, okay, so here this is up and that's down. You have the T-butyl group in the axial position. Okay, the methyl group equatorial. Okay, here if you do the chair flip, now the T-butyl group is equatorial, but you do have to pay the penalty of the methyl group being axial. What you're going to do is you have to sort of take the best of worst cases, right? It'd be great if it was cis, because then you could put them both equatorial, but that's not what we've got. We have the trans version, okay, and so we have to make the best of a bad situation, right, and stuff like that. And so you want the largest group, in this case the T-butyl group, in the equatorial position. So that doesn't mean everything has to be in the equatorial position. You just try to maximize the amount that you can get. Okay, so next up, with constitutional isomers, okay, so for here, what they're going to do is they're going to have this the same formula, but they're going to have completely different connections. Okay, there's also sometimes called structural isomers. Okay, the way that I like to do that is to come in here and start naming them. Go through the 4 steps that we've talked about for doing the naming. Right, find the longest chain. If the main chain is different, then you can stop. You know that they are. You start working down that list of things. As soon as you find a difference, you could stop and say, yep, they're constitutional isomers. You can get to the end and they both have the same name. Well, then they're just conformational isomers. Okay, so like that. So if you've got this one here, right? So here, okay. Oop. Now the first thing you should probably do is just count the number of carbons, right? Because if they have the same number, if they have different number of carbons, well then it doesn't matter if they look the same. They aren't even isomers of each other. Okay, so here we go. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, you can assume that the hydrogens are there, but we have the same number of carbons, so there we go. Okay, so here we go. So that's at least good. Okay, so they're at least isomers of each other. So now we're going to find the same. Right, so with that, so we find the longest chain. So here we go. So 1, 2, 3, 4, 5, 6, 7. Right. So 1, 2, 3, 4, 5, 6, 7. Right. So we can kind of. So it doesn't really matter. Right. So here we go. Okay. So there we go. Okay. So now they both have a methyl group. Okay. Now if we do the numbering, right. So with that, this methyl group's on this side, so it's probably going to start in here. So 1, 2, 3. 4, 5, 6, 7, right? So with that, so same thing here. 1, 2, 3, 4, 5, 6, 7. Okay, so it's going to be 2-methyl. This one's going to be 2-methyl heptane, right? That one's this one too, and so they are in fact just conformational isomers, conformers. Okay, so the conformational isomers, conform. My spelling's bad, sorry. Stuff like that. So these are just conformational isomers. Okay, they have the same name, so therefore they're just conformational isomers. Okay, so for here, now the easiest way for cyclic groups is to say if it's a 6-membered ring and a 5-membered ring, you're done. Stuff like that's easy to figure out. Okay. So here we go. So I mean, this one you can sort of say, oh yeah, they're different, but it's usually good to go ahead and just go through the steps. Because sometimes it's not always obvious. Okay, so again, this one it's a 6-membered ring, right? So that's good, but it has the 6-membered ring and then 7, 8, 9, 7, 8, 9. So they both at least have the same formula. So at least isomers of each other. Okay, they both have this ring. Okay, a 6-membered ring, so that's good. Okay, they both have 3 methyl groups. Okay, that's the same. Okay, now we have to do with the numbering, right? So here, notice how, I should say in this one here, notice how the 3 methyl groups are in a row. Okay, here, there's this group here that separates these guys, the methyl groups. These two are the same, but this one is shifted 1 over. And so the numbering would actually go 1, 2, 3, 4, 5, 6, right? So here it'd be 1, 2, 3, 4, 5, 6. Okay, so this would be 1, 2, 4 trimethyl. and this would be 1, 2, 3 trimethyl. Okay, since the names are different, okay, this is constitutional. Okay. Okay, so what about this one? Okay. Okay, we'll put in our dots for our carbons. Okay, so first step, find the, oh, got to figure out, say, right number of carbons, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we're good there. Okay, but here, right, so we go 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5. And there's no way, right, even if we went down these side chains, right, 1, 2, 3, 4, 5, right, 1, 2, 3, 4, 5, right, we're talking about 5, right, C6 versus C5, right? So this is, we found a difference, so this is automatically a constitutional isomer. Okay? So because the main chains are different. Okay? Okay, last one. This is or I should say, I don't think this is the last thing, but one of the ways that we I do something slightly different than the book is what's called the degree of unsaturation. Okay, they actually call it the index of hydrogen deficiency, which is probably a better name for it, but most people know it as the degree of unsaturation. Okay, and it turns out that the it's when we talk about unsaturation, what we're talking about is a situation where we've removed two hydrogens. Okay. In that case, the way that we do that is either through a pi bond or a ring. Okay, you can sort of see this with here. So if you got ethylene, which is the alkene, okay, this is what's called unsaturated. Okay, for ethane, okay, this is here. This one is just an alkane. Okay, it's this is what's called completely saturated. Okay, so but if you just have all single bonds, that's called saturated. If you have double bonds or triple bonds in there, that's called unsaturated. Okay. Also, if you have a ring, it's unsaturated as well. Stuff like that. But notice how this has two more hydrogens than this one. Okay. Okay. And so the degree of unsaturation really tells you the rings plus pi bonds. Okay. And so all of these groups have the same formula. Okay. It doesn't tell you much. Here you have two pi bonds, right? Here you have a ring and a pi bond, two rings, or in this case with a triple bond, right? Again, that's two pi bonds. Why? Well, each one of these, the first bond that goes on is a sigma bond, right? And then you put additional pi bonds on there. So the second and the third bond on there are both pi bonds. Okay, so like that. So we can come in here and you can look at this, and halides and nitrogens, they kind of complicate the situation. Okay, stuff like that, and you can ignore oxygens in this calculation. Okay, so for that, so there's some quirks as to why. Okay, but but really you can go through this. But really, what I like to do is I like to just say, why don't you memorize that formula? This is one of the few times where I just say, just memorize it. Okay, and it turns out that the formula is 2 times the number of you take a look at your formula, and it's 2 times the number of carbons plus 2. This is a constant. Okay, plus the number of nitrogens, and then you subtract the total number of different halides. Okay, so by that doesn't remember the halides, right? So all occupy this group here: fluorines, chlorines, bromines, iodines. Right. So if you have 2 fluorines, a chlorine, and a bromine, how many halides do you have? You have 4. Okay, it doesn't matter. They all don't all have to be the same, but they all have to be in this row in the periodic table. Okay, fluorine, chlorine, bromine, iodine. Okay, so like that. Okay, minus the number of hydrogens. And you take that number and divide it by 2. Okay. Okay, so if you have C6, H10, NBr. Okay, so like that. So degree of unsaturation, right? So it's 2 times 6 plus 2. Okay, so 2 times the number of carbons plus 2. Okay, plus the number of nitrogens here, right? We have one nitrogen. Okay, and then subtract the number of halides. Here we've got a bromine. Okay, so 1. And subtract the number of hydrogens, 10. Okay. Okay, so this is what? 12, 14, 15, right? 15. minus 11, right? 2, right? So it's 4 divided by 2. That means 2. Okay, so it means we have, so this, right? So the number of rings plus pi bonds, right? Okay, so we could have 2 rings. We could have a triple bond, whatever. Okay, some weird combination of a double bond and a cycloalkane, right? So that's so. Okay, so for here, right? So we can have C5H7NO2, right? Okay, so DOU 2 times 5 plus 2. Okay, so we have a nitrogen. Okay, right? We don't have any halides, so that's a 0. Minus 7 hydrogens, right? All divided by 2. Okay, so this is 10, 12, 13. Minus 7. Okay, all divided by 2. Okay, 6 divided by 2. 3. Okay, so with that, so here again, the number of rings and pi bonds is fine. Now, if you're not, okay, so 0 is fine. Okay, that always freaks out students. If I give them this and it ends up being 0, they kind of freak out. Okay, that's fine. All that means is that it's just there's no rings, there's no pi bonds. It's just all sort of normal carbon-carbon bonds, right? So with that, just regular single carbon-carbon single bonds, carbon-nitrogen single bonds, carbon-oxygen single bonds. Doesn't matter. Okay, that's fine. But again, notice how we didn't incorporate that oxygen into this formula. It's not there. It's not part of the equation. So don't put it in there. Okay, so with that, I'm going to give you this formula. Okay, I'm not going to give you the key, but I'm going to give you that formula in the test. Okay, so with that, but you'll be using it enough that that you'll probably remember it after a while. Okay, and so these are just examples of how you can do it, right? So you can have a cycloalkane, right? So an ammonia, that sort of stuff. Here's an example of a right? So with that, so of something of this formula. Okay. Okay. Right, so you have a ring, that's 1. You have and then 2 pi bonds. I never said that they had to be carbon-carbon pi bonds, right? So here we have a carbon-oxygen pi bond, right, for that double bond. And here we have another double bond, right? So each one of those has a pi bond, right? So pi bond, pi, and then ring, okay? So those are your 3 degrees of unsaturation. Here you got the ring, and you have the 1 pi bond there. So that's 2. Okay. So there we go. Okay, so drawing constitutional isomers. Okay, so this is so if we turn it on its head, remember we were talking about are they? Now the question becomes how do you draw them? Okay, so the first thing to do. So let's say we have so C4H8F2. Okay, usually the first thing you're going to do is actually do a DOU calculation, right? So remember, is it a are there any rings or any pi bonds or whatever, stuff like that. So here it's 2 times 4. There's no nitrogens, right? So 0, but there are 2 halides, right? So there's 2 fluorines, okay? So right, minus 8, okay? So all that divided by 2, right? So oh, I forgot the plus 2. Oops. Okay, so this is here. Let me do this again. 2 times 4 plus 2 plus 0 minus 2 minus 8. Okay, I can't forget that 0, that plus 2 there. Okay, so this ends up being 10 minus 10 over 2, 0. Okay, that just means there's no pi bonds, no rings. So it works out well. Okay, so the easiest thing to do is to just say, okay, I usually start with the longest straight chain that I can get away with, and then shrink it down as needed. Okay, stuff like that. And so what I usually do, okay, is you say, okay, let's put those carbons in a row. Okay, so that's the easiest thing. Okay. Okay, so what we do is you start with the carbon framework, and then we'll put fluorines on there. But the other way that you could, right? So we're going to sort of move this down, right? So we're going to separate this because there's another way we can do the carbon framework. But I wanted to sort of show this, right? So we can put, let's say, both the fluorines here. That's fine. So let's say we keep one of these fluorines here. We're going to move that down the chain. Okay, so we can sort of be systematic about here, right? So we can put 1 fluorine there, 1 fluorine there. That's good. Okay. Right, so fluorine, I'm sorry, put the fluorine there, right? And now we do fluorine. Okay, so I'm actually going to label these like A, B, C, and D, just so it's easier to talk about it. Okay, so now let's start with, okay, so let's put the first fluorine here, and let's keep that the one that we're fixed. Okay, so then it becomes here, okay, That's the fixed one, right? We're going to put that fluorine there. We're just going to move the one we moved, just move that down the line. Okay. We're going to move that there, there. Okay. Here and here. Okay. Now, so then what we could do is we can say, okay, let's put that fixed one here, okay, and then move that one here, okay. But what's the problem? Okay. Well, here we go. Okay, so let's just go ahead and make them all. Okay, so again, we're going to have this one fixed. Okay, here. Just you can do like all the possibilities. Okay, so we have that fixed one here, right? And then this one there, and then this one there. Okay, and the last one, last set. We're just going to be systematic about this. Okay, we're going to put the fixed one here, 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 and here, and then have this one have one move here, here, oop, and then here. Okay, the problem comes, okay, so D, E, F, G, H, I, J, K, L, M, N, O, P. Okay, the problem comes is if you were to take this one, okay, so if you start looking at, these are going to be fine. Okay, if you take this one is actually the same as B. Okay, so we don't need that one. This one here, well, that's unique. Okay, we both have them on 2, so that's fine. This one here, that looks okay. Looking at the ones above it, that looks fine. This one here is actually the same as C. Okay, if you take this one and flip it, it turns into this one, so we don't need this one. Okay. Here, again, this one I, right, is just the same as this one. Again, this is the one that's just C. This one here is the same as G. Okay, so we don't need this one, don't need this one. Here, this one is the same as F. Okay, so we don't need that one. Okay, this one is just the same as this one, right? You just take this and flip it, okay, and it turns into that, right? So this is B. Okay, so you can be really systematic about this, but then you got to cross things out that are the same. Okay. Here again, you've got these at the ends, right? Well, we've already seen that up here, so that's D. Okay, so we don't need that one. Here, one and here, that's the same as C. Okay, so we don't need that one. Here, 1, 2. Okay, well, that's the same as B. And then these, that one, that's just the same as this one, right? Just flipped. Okay, so here. Okay, so these, so you have A, B, C, D, F, G, and that's it. All the rest of these are going to be duplicates of ones you've seen before. Now, it doesn't matter. I don't care which ones you pick, so like that, as long as each one is unique. Okay, so but you can be systematic about that and just cross them off as need be. Okay. Okay, so these are the ones with the straight chain on it. Okay, so the thing to do is to say, okay, I'm gonna lop off that carbon and stick it somewhere to make it somewhat shorter. Okay, so you have the C right there, right? So let's put that C there. Okay, the other option is to put it there. The other option is to put it there. Okay, the problem is, notice how the main chain here is like this, right? We can go down there, here and here is just the same as that, right? So it's just a regular butane. Okay, so we can't use these because these it's just literally this. It's just we've taken the carbon and just rotated it down. Okay, stuff like that. So this is the other framework that we can work with, and so we can go with. Right, so we can keep one of them fixed. Well, let's do the fixed one in blue. Okay. Move that one around. Okay. Okay. So we're going to put one fluorine here, one fluorine here. This is going to be our fixed fluorine, and then we can put the movable fluorine here, 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 or here. Okay. Now the problem comes. Okay, so here we have both the fluorines and one carbon. Okay, here we have them one next to each other. So that's okay. These are different. Okay, here the problem comes with these two. Okay, so if I do the main chain here, right, we have fluorines on the outside and a methyl on the inside. Right. Well, if I just do the main chain like this, right, we'd have fluorines on the outside, carbons on the inside. Okay, so we don't need this one. Okay, the other option would be, let's say we put the fixed fluorine there. Okay. Okay, so let's be systematic about this. Fluorine, 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 fluorine. Okay, all of these guys here, all three of these are the same. Okay, so if you have, you sort of here, fluorine 1, fluorine, carbon 1, carbon 2 on the fluorine, carbon 1, carbon 2, carbon 1, carbon 2, and then off this one, right, we have 2 methyl groups. Okay, so these aren't needed. Okay, this one, however, is unique. Okay, and if you did it down here, right, stuff like that. So here you've got these guys there. So you have the ones from here and the ones from there, and there you go. So, but this is really hard. There's a lot of them with this one, and the fact that they're fluorines makes them, you have to be careful about being able to flip them, stuff like that. But the thing to do is usually to start with the longest, especially if you have a straight chain. Start with the longest straight chain, and then start pairing it back. And and you can be systematic about it, stuff like that. But you just have to go back and see if there's another one up there, stuff like that. So just be careful. Okay. Now on the exam, what I usually do is I usually put some sort of functional group on there, so there's not going to be like 80 of these things to draw. Right? There's usually 3, 4, 5 to draw, and that's fine. Stuff like that. So it pairs it down a little bit. Okay. Now for something like this, okay. So here's another one. So C3H6O. Again, we're DOU. Okay. So we can do. Okay. So here we go. So 3 times 2 plus 2. You don't have to. There's no nitrogens, right? So plus 0. There's no halides, 0. But there is 6 hydrogens, right? All divided by 2. Notice the oxygen isn't put in there. Okay, so 8 minus 6, all divided by 2, so 2 over 2. So there's 1, right? So we have a ring, or we have a double bond, a pi bond somewhere. Okay, so the easiest thing to do, right, is to go in and say, okay, well, let's start with the ring. Okay, so we can do a ring like this. Okay, and we can put the oxygen out. Okay, so and if you count this up, right, we're actually missing a hydrogen, right? So with that, the oxygen, the hydrogen would actually go here. And remember, what does oxygen like to have? It likes to have 2 bonds and 2 lone pairs. Okay, and so it's either going to have a carbon-carbon bond, or it's going to have a carbon on one side and a hydrogen on the other, or it's either going to have a carbon on one side, carbon on the other, or carbon on one side, hydrogen on the other. Okay, unless we start doing double bonds, we can't do that because our DOU is taken up by the ring. Now the other thing we could do, right? We can put the oxygen within the ring. Okay, just swap these two. Okay, and put a carbon out. Right, so we can swap the positions of the oxygen and the carbon. Right, so now, right, the oxygen has 2 bonds, so it's happy. So that's there. The other thing that you can do is you can just put them all in the ring. Okay. Like this, right? So there we go. Okay. Now you can say, well, why don't we put the methyl group over there? Well, we could. That's fine. But my drawing's kind of bad. But if you just take that molecule and flip it up like that, it turns into this. So we don't need that. Okay. The other option. Okay. So there we go. So we've got okay, so these are the possibilities for the ring. Okay, but we also talked about straight chain, right? So we could put them all in a row. Okay, and so we could say, okay, well, let's put the oxygen, put the OH there. Let's put the oxygen there. Okay, we could do it like that, or we could put the oxygen there. Okay. The other option would be to put it in this strand, right? Or in the main chain, right? So it would make an ether. Okay, so that'd be okay. So now we have a couple of options. Okay. The first one being, right, so we can put the, so these are at least the backbones for it. Okay, so we can either do, so for this one, we can either put, say, that the double bond there. So that would mean that the OH and OH was there. Let me move this out of the way. Okay. We could put the double bond there. That's okay. Okay. Or we could put the double bond there. Okay. We can either put the double bond here, put the double bond there, put the double bond there. That's fine. That's good. We can do that. Again, we can either put the double bond there, double bond there, double bond there. Right. So put the double bond there. We can put the double bond there, or we can put the double bond there. Okay. Now the problem is, notice how these two are just the same molecule; they're just flipped. Okay. So let's say we don't; these two are the same, so we don't need one of them. Now the other option would be to, remember we talked about, we could put the you can't put the OH here, right? Because that's just this. Okay. So these are the sort of base structures. Okay. You can go with. Okay, we can't put the double bond there, right? Because we said that the double bond likes having right. The oxygen likes to have two bonds and two lone pairs. Well, so we don't want to put the double bond here or here. So really, the only place that we could put it is here. Okay, because otherwise it would cause the oxygen to have a formal charge on it. Okay, so there we go. So we have these rings, and then we've got these straight chains here. But we have to be careful because these two, those are that, right? So these are our base structures. Okay. So you just try to be systematic about it. Okay. So there we go. Good luck.